Hello, thank you for coming to today's joint webinar hosted by the Monitor and Tiger project. We're going to be looking at today improvements to reliability modelling for tidal turbines. I'm Michael Tinieri from the University of Swansea, the PI on the Monitor project, and I'm going to run down some of the introductory stuff for today's event. Start with an introduction to the agenda to the event. We're going to have introductions to both projects delivered by myself and Philip Tees for the Tiger project. Alistair MacLeod from ORE Catapult is then going to give us a summary of the main reliability model that we use in the Monitor project. We're going to have a case study from the Tiger project delivered by Philip. Then we'll have Miriam Slama from University of Le Havre and Yesterday Evans from Swansea University, talking about the lab and numerical work that feeds into Alistair's main reliability model. We'll have a second case study from Tiger delivered by Stuart Walker from the University of Exeter, and we'll finish up the presentations with Andrew Pacheco talking about the at-sea measurements on full-scale turbines and how we can use that to predict reliability more generally. We'll finish up the event today with a Q&A and panel discussion. Now, you should, at the bottom of your screen, see that there are two channels, a Q&A channel and a chat channel. If you have any questions for the speakers, please do put this in the Q&A channel. We will keep an eye on this and we'll try and answer questions that we can as we go along. And any that we think merit a particular discussion by the panel, we'll bring into this 50-minute session at the end. Other things to be aware of is that this webinar is being recorded and the recording will be made available to everyone once it's all been processed and so on. And you should get an email from Carly, who has organized this event, who will let you know when it's available, when you can where you can download from on each of the project websites, along with a link to download all the presentations and a chance to sign up to each project newsletter. Now, I've left myself a good 15 seconds to introduce the Monitor project, so I'll do that very quickly now. Monitor is a multimodal analysis of tidal reliability. It's supported by the Interreg Atlantic Area project, and the partnership involves a collaboration of academia and industry. You can see that along the bottom there. And to give you a very brief idea of what it is we're looking at reliability of tidal energy converters, particularly with a focus on the blades and the structures, so the big bits of metal rather than the internals. Using a multi-model approach, so we're trying to tie in all the sources of data we have through a single reliability model, so to get as much of the data we can access and feed it into a single way of predicting how reliable things will be. And we think this is very important for the tidal sector because, as we can see from this report from ORE Catapult from 2019, operations and maintenance is the single biggest technical cost associated with tidal projects at the stage we're at, with kind of individual devices and small pilot farms. Okay, I'm going to stop there to give Philip some chance to introduce the Tiger project. So Philip, if you'd like to take over at this point.
Thank you, Michael. I found the unmute button, I found the share button. Good morning, everyone. My name is Philip Tees. I'm an associate professor in renewable energy at the University of Exeter. And I'll kind of present the Tiger project in about 2 slides. So it's an Interreg project bringing together partners from the UK and France on both sides of the channel. It is, in fact, the largest ever Interreg project, so a big bang to the end, with an overall project budget of 45 million euros. So it's really a big push from both sides of the channel to advance the tidal energy sector, to get deployments at a total of 5 sites, which you can kind of see on the map here, and is really trying to demonstrate both the economic and the social benefits to the coastal communities on both sides, to really advance the tidal sector. It's a joint project between academia and industry and kind of some organizations in between. So the there's a total of 18 partners, almost too many to put on one slide, but you can see kind of on the industry side, there's a range of different turbine concepts. There's all tidal stream, as well as end users. And really the aim is to allow those companies to deploy at the different sites to advance their commercial readiness with some of the academic and scientific inputs we can provide as from both sides of the channel as well. So the project will run until 2023. Currently, we're out doing ADCP and resource measurements, but you'll see news on deployments very soon, I hope. That's it for now, and I'll talk to you later.
Okay, we've got Alistair next, talking about the variation mode and effect analysis model of reliability.
Thank you, Michael. Hello, I'm Alistair MacLeod. I'm the Mechanical Engineering Team Lead at the ORE Catapult. The ORE Catapult is the leading technology and innovation research centre for offshore renewable energy in the UK. We use our unique facilities and research and engineering capabilities to try to bring together industry and academia to drive forward innovation in renewable energy. We've offices across the UK, and I'm based in Glasgow. So I'm going to spend the next 10 minutes or so introducing what we're doing on the Monitor project, which is the VMEA tool, and talk about how we're bringing together that modelling and delivering our work package. I'll introduce the concept of VMEA, which stands for Variation Modes and Effects Analysis, give a bit of background on how it was developed, what we aim to do, and how we might use it. I'm aware not everyone will be too familiar with VMEA, so before I go into what we're doing on the project, I'll give a little bit of an overview of what the process is. So we're leading work package 4 of Monitor, the development of the VMEA reliability modelling tool. The project is focused on blades and support structures of tidal energy converters, and we want to identify and model the crucial design and load factors which influence reliability of these components. We're going to first apply VMEA to Sabella Magiennis' devices, to 2 intentionally very different devices, and then use this experience to help develop and test generic VMEA models, which will be useful to a range of tidal energy developers. We're keen that the tool is useful and as relevant as possible. We've got about a year left on the project, and we're currently really getting stuck into kind of going through the VMEA process. So VMEA, what is it? Why was it developed and why use it? It's essentially born out of FMEA and is based on the idea that when we consider the potential failure modes, and these are always caused by unwanted or uncontrolled variations somewhere in the system, and to avoid these failure modes, we must either control variations in some way or ensure that the designs are robust enough to stand up to these unavoidable variations. VMEA was developed to assess and improve this robustness. It was first developed in the early 2000s and has been used in much more mature industries such as the aerospace or automotive industries for 10 to 15 years. I should note that on Monitor, we're building on a body of work previously done on RISR 1 and 2, which investigated how VMEA could be adapted and used on marine energy converters. As part of that project, a guidance document titled Reliability Guidance for Marine Energy Converters was produced, and I reference that a fair bit and we'll refer to it today. By more accurately predicting loading and understanding sources of variance, we can de-risk tidal energy development by improving reliability. Specific things to note about VMEA: it systematically assesses the influence of input uncertainties or noise on device or component performance. Many current standards and guidances use characteristic values of load and strength and safety factors to establish design values. These partial factors account for uncertainties and reduce probability of failure, but are difficult to set for new technologies, particularly tidal energy converters without much prior knowledge. VME approaches this problem differently by accounting for uncertainty in the analysis. It's not intended to replace existing reliability tools, but as an additional method of improving designs. A basic FMECA should be carried out initially to determine where to spend time and effort on a VMEA. Because of the way VMEA treats uncertainties, it can be used to help derive appropriate safety factors for target life. For example, potentially reducing over-engineering or highlighting where design improvements could be made. So there's quite a bit of detail on this slide, but I want to highlight here that there are three different approaches or three different stages to the VMEA, and which are commonly referred to. These are a basic VMEA, an enhanced, or a probabilistic one, which is the detailed one. The main difference really is how much information is available and which stage of your design process you're at. All three of these VMEA processes follow the same steps, and we're using the steps as defined in the RISR guidance on the Monitor project. Some previous work looked at 4 or 5 steps, but essentially it's always done in the same way. In the next few slides, I'll go through these steps in a bit more detail. So the first thing that should be done is target variable definition. So looking at a particular component or a particular characteristic, for example, ultimate strength, total damage, or fatigue life. In Monitor, we're looking at blades and substructures. So we'll be performing VMEA on both devices on separate components. If we imagine for now, we've taken a tidal turbine blade as our component and the fatigue life as the variable we're most interested in. What we now need to do in step 2 is identify all sources of uncertainty related to calculating the fatigue life of a blade. One key thing to note is that calculation for VMEA should use expected values rather than conservative estimates, or the use of partial or full safety factors within the calculations. For example, some of the process to estimate fatigue life is shown. Understand loads, convert these loads to forces, convert forces to stress, and finally use a fatigue model to understand the blade fatigue life. We need to estimate the sources of uncertainty each stage of that calculation. Some examples are shown. And don't suggest that these are all the sources of uncertainty or the right way to calculate fatigue life. It's just an example. Next, for each of the uncertainties, we need to determine both its size and the sensitivity of the target variable to its change. So how uncertain are we, and how sensitive is the thing we're considering to how much that thing varies. The uncertainties will be entered into a table like the one shown here, and in some cases the uncertainties can be split. The uncertain components will be split into scatter and uncertainty. But for this example, I've simplified the process a little just to show the basic mechanics. Then for sensitivity, step 3, there are a number of different ways to do this. For example, we can use prior knowledge and judgment, we could do parameterized modeling, or a range of kind of physical model tests, full, small scale, whatever. Monitor will use a range of model and test data to try to quantitatively assess sensitivity values. And then on to point 4, uncertainty size assessment. To determine the size of an uncertainty, usually the standard deviation of a data set is used. That could be fatigue strengths or significant wave heights or something. Then we calculate the uncertainty for each line item. And that's a case of multiplying the size and the sensitivity, also known as the risk priority number. The total uncertainty is then summed. From this, we can then identify areas which contribute significantly to the overall uncertainty. There are also ways to assess the safety factor, but I'll not go into that just now. Again, I would refer to the RISR material in the first instance when reading up on this stuff. And then finally, we use the results of the VMEA to identify actions to take. And those could be design changes, further studies, or more testing to reduce our variations and uncertainties. And then steps 6 and 7, reliability and robustness evaluation and improvement actions aren't generally considered in a traditional VMA process, but we've included them in this work. And this is a schematic of how we're currently applying VMA on the Monitor project. So on the left-hand side there, we have a range of inputs from environmental conditions recorded at sea or through modeling, and we've device inputs, be that operating curves, sort of estimations of start stops, that sort of stuff. And we then have the components we're considering. So that would be blade geometry or its material properties. And then that's our kind of final input, is things like yield strength and the SN curve. This all then goes into various models for load history, calculating stresses and strains, and then all this feeds into our fatigue behavioral model. So hopefully that's given you a sort of high level understanding of what the VMA process is, and how we're applying it at the moment on Monitor. We've got around a year left, and we want to develop the model into something that can be used by the wider industry to assess where we have these variations and uncertainties in designs. Thank you very much.
Okay, thank you, Alistair, keeping the time beautifully there, which actually made back some of the time that I took up in the introduction. So thank you for that. And that gives us time to transition over to Philip to introduce the first of the test cases from the Tiger project.
Thank you, Michael. I hope you can see that screen correctly and hear me well. So thank you for the introduction. Whilst it's being introduced as a case study, I should say is being done as part of the Tiger project, but because we're in the stage of actually with industry partners planning installations and getting turbines out, we started well with a good old academic practice, which is to review what has been currently done, and actually realizing that there hasn't been much work on actually reviewing all the tidal energy projects that are out there. That have been reported on, to see how they've fared, have they kind of met the expectations, and if they've been curtailed or failed, what were the failure modes for that? So as always with these things is obviously not just me. So the main credit for actually doing the detective work and finding out all the references and some of the press releases. On those projects, so it's Dr. Stuart Walker. You'll hear from him later for another topic, but he's done most of the legwork, and then we work together in analysing that data set. So I'll present briefly kind of an overview of the deployments and the data set that we base the analysis on, to then look at the performance and the reliability of those projects. And I should say, kind of in terms of failures, because as you'll be aware, that there's no kind of detailed failure investigation report that's been made publicly available, although I would like to see that in the future. We kind of refer to failures as on a project level. So was the project successful, or did it fail, or has it been curtailed? And looking at that data set, really, we were trying to figure out, well, over time, do we see reliability growth? Do we see an improvement? And what are the trends there? So I'll go through those in 10 minutes. So we work to the classification for tidal stream technologies. So looking at the ducting, the extractor type, the foundation type. So is it floating or fixed, and what type of foundation is there? Overall, so over almost kind of over 20 years, from 2003 to 2020, that should say, we've reviewed 57 projects in total. So quite a substantive data set. And I'll present some of the highlights here in terms of the data and what type of devices there are, because there's some interesting insights with that regard. So this first slide, if we look at the number of turbines and the kind of foundation type that's been used, you can see that the overwhelming majority, as you'd maybe expect, is one device. So we're looking at demonstration type projects, but there've been around about 10 installations with 2 or more devices as well. So there's a few examples of that. Again, if you look at the legend here, mostly horizontal axis turbines. And on terms of foundation type, there's a kind of mix you'll see later in the time series. There's some interesting trends there, but it's an even mix between floating and fixed foundations. And then historically, I think you'd probably expect that as well, that there's a majority of kind of fixed foundation. If we're looking kind of how long have those projects been deployed, again, the theme with the kind of demonstrator project short deployment times continues here. So the majority is kind of 1 or 2 years of duration. But there's a few projects that have kind of 5 years and more. And obviously all of this is kind of anonymized, but you can, if you're in the industry, you can guess who's who in those data sets. Looking at project performance then, so the good news first, the overwhelming majority is successful as a project, so meeting kind of the performance delivery that's been set out at the beginning. There's a few that have underperformed, so maybe not quite delivering the energy yields, and then there's a few projects that have been curtailed, so cut short, and most of this category was due to underperformance. Some stated fatigue issues, and then there's a kind of the top ones here. These are the projects that have failed. And what's interesting, we've just heard about blades. So this has been the majority of failure statements, or the main reasons for it, followed by kind of monitoring and generator issues, as well as problems at the installation itself. So there's a range of kind of reasons for project failure. What is interesting to see, if we look at the foundation type, and we've got floating mooreds, fixed, with the different types here. What you can see immediately, kind of the failed projects are only in the fixed foundations. And you could argue that for floating mooreds, that's kind of being replaced by curtailed, because you'd obviously tow the device from its site, so you curtail the project rather than fail it entirely. So there's certainly benefits here for the floating installations, that if you have issues, you can recover and hopefully fix it. Also interesting to look at that data set over time. So some successful projects back in 2003, and then what seems like a bit of a rough patch, 2006 to 2010, lots of issues in those projects. Some of our analysis suggests that kind of within the industry, or within the companies were trying to get too big too quick in terms of installed capacity and project ambitions. So there's a little bit of setback here, with the project not going as planned, but actually as a sector goes, kind of good recovery in 2011, and then the majority of projects perform successfully. A bit of underperformance issues here, but overall you can see that the kind of the green bars are increasing. We've tried to summarize that and kind of reassess that data set from a reliability growth perspective. So that the classic reliability growth model would work with kind of either installed capacity or total amount of operating hours, and then you're looking across the actual number of failures that you would see for the overall system or for some of the subsystems. With the data set and the information that we've had, we related that to, again, number of project failures. So on the left, on the y-axis here, in terms of percentages, you can see kind of early on, if the dashed line here, the black dashed line, that's all the projects together. So around about 600, estimated 600,000 operating hours, about 60% of the projects failed. But over time, and actually with an increased amount of operating hours in the projects, so the last kind of data point we could make out is around about 1.2 million operating hours. You can see kind of the percentage of project failures by then for the overall drops to 30%. So over time, I think actually this is a really good demonstration of the fact that there is learning in the sector, there is reliability growth overall on the project level. It's obviously then interesting to see where within the devices does that take place, and what are the main kind of technical issues in those subsystems. But hopefully that's the more detailed level that we get to in the project, we hope. So to kind of summarize and conclude, and maybe actually look beyond the status at the moment. So the kind of the data we've reviewed, that was more than 30 megawatts of tidal stream capacity. Still, there's a multitude of concepts which, from a reliability perspective, is kind of causing kind of the analysts, me and Stuart, a bit of grief, because you want convergence ideally to have a nice data set, i.e. kind of 3-bladed horizontal wind turbines. Once the design is converged, that makes for a better data set and kind of helps the sector. That's difficult for tidal. I think there's remit in those different concepts, so I don't see them converging anytime soon. Overall, kind of it's still pre-commercial, and hopefully Tiger will push that towards kind of a more commercial level. But with the slide just before, I think the reliability growth is demonstrable up to now, and hopefully further with the deployments that are underway. A comparison with onshore wind. So this is a plot from Falstich and others at Fraunhofer. They did they've got the reference data sets for the onshore wind turbines in Germany, and it's interesting to see that for the kind of the operational hours we've got at the moment, and comparing that with onshore wind, because sometimes those comparisons go as 10 or 20 years. So onshore wind had kind of 1 million operating hours around about 20 years ago, but the failure rate was a lot higher as well. So there's growth both with years of operation, but also years of production. So the number of iterations you do in the prototypes. So that's a useful comparison we find to really look ahead, and that learning takes place as we deploy more. Obviously, acknowledgements to Tiger, and you can find Tiger on Twitter there as well as the webpage at the bottom. And as I said, the paper is currently under review, so hopefully you'll be able to read the full story very soon. Thank you very much, and I'll stop sharing.
Okay, thank you very much, Philip. I'd now like to hand over to Miriam Slama from University of Le Havre to talk about some of the laboratory work that's been done under the Monitor project.
So thank you for the introduction, Michael. So I'm Miriam Slama from Le Havre University, and I will present the lab work carried out in the framework of the Monitor project. So this study was carried out with partners from the project and people from the Ifremer at Boulogne-sur-Mer. So first I will describe the experimental setup, then I will present quickly a few results for the performance evaluation, blade workloads, and spectral analysis. So it's just a few results to show examples of what kind of post-processing we did and some of the conclusions that we obtained. So first, the experimental setup. So 2 industrial prototypes were considered for the lab testing. The first one is the Magallanes Renovables floating platform, so ATIR, which have 2 rotors with 3 blades each. We can see on the top figures a representation of the ATIR, and on the right we can see the scale model used for the lab testing. So only one of the rotor was modeled for this study. The second prototype is the D12 turbine from Sabella, which has 5 blades. And here again, at the bottom on the left, you can see the scale model. So we have 2 devices with different blade numbers, different blade profiles, and different blade materials for the 2 scale models. All the tests were carried out in the Ifremer wave and current float tank in Boulogne-sur-Mer for 2 weeks in 2018. So you can see on the right at the top a schematic side view of the experiment configuration, and below you can see the corresponding photo taken during the test. The flow conditions were monitored with laser Doppler velocimeter and an acoustic Doppler velocimeter. The ambient turbulence intensity in the float tank can be regulated with flow straighteners, which are placed at the inlet of the working section of the float tank. And for tests with waves, we used also 3 wave probes and a piston type wave generator. Load measurements are made directly on the scale model with a torque and thrust sensor placed on the rotor axis of the model, and 5 components load cells placed at blade roots. So here on the left, we can see a scheme of the blade root load cells with the torque and thrust transducer. There are only 3 load cells. So for the ATIR model, which has 3 blades, each blade was equipped with a load cell. For the 5-bladed D12s, blade support were manufactured in order to adapt the 5 blades to the load cell. So with 1 support for 1 blade and 2 supports with 2 blades each. We considered different flow conditions for the test. So the first were current only conditions, then current and wave conditions, but I will only present results for the current only conditions today. So there were several upstream velocities and 3 turbulence intensities, so 1.5%, 3%, and 15%. Some other data were already obtained by the Ifremer during previous testing campaigns, so for their generic turbine. And we use some of this data in order to compare the result obtained for the D12 and the ATIR. So in this database, 2 turbulence intensities were considered, 1.5% and 15%. So we are able to do comparison for 3 different scale turbines with different rotor design, blade numbers, and materials. And I didn't show any picture of the scale turbine from the Ifremer, but it's a 3-bladed turbine. Now I will present some results for the power and thrust coefficients. So I will show comparison of the results obtained for the 3 devices. And so all the results I'm going to present now are normalized for confidentiality reasons. And on this figure, we can see the time average power and thrust coefficients plotted against the tip speed ratio obtained so for the 3 devices, the ATIR, D12, and the Ifremer turbine for several upstream velocities and 2 turbulence intensities, so 1.5% at the top and 15% below. So for the time average power and thrust coefficients, we can see that the ambient turbulence intensity have little influence on the results. We can see some differences. The power and thrust coefficient are slightly higher for the ephemeral turbine, but that's all. But the ambient turbulence have a large influence on the standard deviation of the power and thrust coefficient. So on this slide, we can see the standard deviations of the power and thrust coefficients, again for the 3 devices and 2 turbulence intensity. And we can see that there is a large increase of the load variations with the turbulence intensity. For example, if we look at the standard deviation for the power coefficient, for a tip speed ratio between 3 and 5, we can see that the load variation are multiplied approximately by 5 when the turbulence intensity increased from 1.5% to 15%. We can also see some differences between the curves obtained for the 3 devices, but the shape and the value are really similar. So the rotor design does not seem to have a large influence on these load variations. However, the same drivetrain was used for the 3 scale models, so maybe it has a large effect on the results, and it may hide some differences due to the rotor design. So this will need further study. If you want to see more results and details about this, you can take a look at the paper written for the UTEC conference in 2019, where there is also some results for the power and thrust coefficients with current and wave conditions. We have also submitted a paper to Ocean Engineering, and it is still under review, but hopefully it will be published soon. Now I will show a few results for the blade root load variations. So here we can see the phase average blade root loads for the ATIR model obtained for a turbulence intensity of 1.5% and a tip speed ratio of approximately 5. On the left plot, we can see the phase average loads for the axial forces. And on the right, we can see the phase average edgewise bending moments. And for the bottom plot, the angular position for blade 2 and 3 were adjusted with plus minus 120 degrees. And we can see that the curve superimpose well for the 3 blades of the ATIR. Particularly for the axial phase average axial forces on the left. There are a bit more differences for the edgewise bending moments, but the curve collapse. We can also see that the load variations strongly depend on the blade angular positions. For example, for the axial forces, we can see 2 maxima and minima, which are reached when the blades are almost vertical or horizontal. For the edgewise bending moments, the load variation are slightly larger, but this is due to the weight contribution, which wasn't removed from these results. And the variation of the edgewise bending moments are similar to the evolution of the weight contribution of the blades. We also studied the first phase standard deviations of the blade root loads, and we compared the results for the 3 devices. So to do that, the load variations were evaluated for the whole tip speed ratio range for 3 turbulence intensity cases. And in order to synthesize the results, only the maxima of the phase standard deviations are compared. So on this figure, we can see an example of the phased average axial force on blade 1 for the ATIR model with the field area, which corresponds to the phase standard deviation. And for our comparison, we only considered the maximum value of this phase standard deviation. So on this slide, we can see So the comparison of the phase standard deviations for the three devices with the maxima of the phase standard deviations of the axial force on the left and the maxima of the phase standard deviations of the edgewise bending moment on the right. So the results were obtained for 3 turbulence intensity for the ATIR and D12 and 2 turbulence intensity for the Ifremer. We can see on the left that for the axial forces, the load variations evolve similarly. So we can't really see any impact of the rotor design, but only an increase with the turbulence intensity. For the edgewise bending moments, the load variation are increase with the turbulence intensity, but there is clearly an impact of the rotor design on those results. So for more details, you can take a look at the paper written for the conference Renew from last year. And finally, I will show you a few results for the spectral analysis, and more particularly for the magnitude squared coherences. So the magnitude square coherence for 2 signals is defined like this. And on this picture, we can see the magnitude square coherences between the torque and the axial flow velocity on the left, and between the torque and the rotational speed on the right. So these results were obtained for the ATIR model for 3 turbulence intensities and 2 tip speed ratios. What we can see is that at low frequency, the load variations, the torque variations are related to the flow velocity. But at high frequency, they are driven by the rotational speed control units of the model. We also compared these results for the 3 devices, and what we can see on this picture is the comparison of this magnitude square coherence between the torque and the axial flow velocity with the blue curves, and between the torque and the rotational spin with the green curves for the 3 models, and for a turbulence intensity of 15%. And for this turbulence intensity, we can see that the coherences between the torque and the axial flow velocity are not impacted by the rotor design. And for the coherences between the torque and the rotational speed, there is an impact, but only at high frequencies. So to conclude this short preview of what we obtained for the lab testing, we saw that the ambient turbulence has an important impact on the rotor and blade load fluctuations. The rotor design does not seem to have a major influence on the rotor load fluctuations, but this needs further study because we use the same drivetrain for the 3 scale models. So we will do a 3rd week of testing next month in order to evaluate the impact of the drivetrain and also to complete the study of the influence of combined currents and wave conditions. So thank you for your attention.
Okay, thank you very much, Miriam. It's some interesting and quite in-depth analysis of the results there from the lab work that's been done at Le Havre and at the Ifremer facility. So if we can hand over to Jestin now to talk about the numerical work that's been done. I look forward to hearing from you, Jestin.
Brilliant. Thank you for the introduction, Michael. I'm Jestin Evans and I'm a research assistant at Swansea University. So I'm currently working on the Monitor project, specifically work package 5, which is the numerical modeling of a tidal stream turbines. I'm specifically working mostly with blade element momentum theory. So the blade element momentum theory can predict turbine performance and loads, which we directly feed into the VMEA model as you've been described earlier on in the talk. It's a computationally efficient method, So for example, the computational demand of a typical short 10-second CFD simulation, we would be able to produce thousands of BMT simulations. This allows us to have a greater data set and have more data to work with to improve the reliability. So the method combines two numerical theories, the momentum and blade element theory. If you're interested in learning more, please look at the cited references. So modeling the turbine rotor in the BMT model, the first step is to split the rotor blade into elements. Each element then is given a radial position, a twist, and a chord data, which is imported into the model. We also import hydrodynamic properties, which is lift coefficient against angle of attack and drag coefficient against angle of attack. From this data, we work out the loads for each element and simply sum them to predict the whole rotor performance. So the BMT model's accuracy is only as good as the flow field we use. So care must be taken in choosing the most, care must be taken to choose an appropriate flow field. We have 4 types of flow fields we can use in our model: uniform, power law, a file, which can be data, ADCP data taken from real site flows, and synthetic turbulence. So synthetic turbulence, we can reproduce a statistical model of the flow fields without the need for expensive computational physical precursor simulations, which is important as the BMT model main strength is the computational efficiency. In the monitor work, we use synthetic eddy method and Sandia methods to produce a synthetic turbulence. We've seen that the synthetic eddy methods scales better at large and more detailed flow fields. But we've noticed that at high frequency, the spectral features can be poor. But we've improved this by allowing for variable length scale eddies. Looking at the variability with synthetic turbulence across different turbulence intensities, the plot on the bottom left shows how coefficient of power against tip speed ratio varies at high turbulence intensity 15, which is the big error bar, and against low turbulence intensity, which is 3%, the low error bars. As expected, the higher the turbulence intensity, the more fluctuations and variability we're going to get. The plot in the top right shows a linear correlation between turbulence intensity and variability in both power coefficient and thrust coefficients. We've noticed that we underpredict the fluctuation compared to experimental data. And we've also noticed that an agreement in velocity spectra does not always imply that there's going to be an agreement in the load spectra. So what can we do with our models? We've got 3 main types: a steady state, transient, and a specific blade model. The steady state simulations, we can model a single rotor over a range of tip speed ratios against various parameters, such as coefficient of power and thrust. The transient model, we can simulate a rotor in a flow field over a defined period, again, for different parameters. And our final model, we can solve the BMT equations for a single rotor at a specific fixed tip speed ratio. And we'll get output values of loads for each element. This is can be really useful for debugging and for investigation purposes. The limitations of our model is that we can only model a single rotor. We can't look at interactions between multiple devices and no array modeling. To make it a computationally efficient method, we've also made several assumptions which neglect the physical phenomena of tip vortices and radial flows, just to name a few. So it requires the inclusion of semi-empirical corrections to deal with these omissions. This slide shows what we can do with the third model I described there at the specified tip speed ratio. So it shows how we can get elemental parameters across the radius of a rotor blade. The plot on the left shows how the torque contribution varies across the radius of a rotor blade depending on the operation condition, from stall to optimum to overspeed. Improvements to the BMT model that we are currently making is by improving the representation of a blade. So the old model, all elements were assigned the same hydrodynamic properties, which is based on the average shape of a rotor file. In our improved model, each element is assigned its unique hydrodynamic properties, and this is based on its geometry, but also the Reynolds number at that element. We've seen at optimum rotor performance that an increase in accuracy of 20% is seen between the BMT model and laboratory data. We've done a comprehensive comparison to laboratory data across various flow speeds and turbulence intensities, and the results are promising, and it shows that the BMT model is capable of representing and matching the laboratory data close. Further work we will hopefully have at-sea data to compare to. Additional numerical work that's been carried out on the monitor project is the vortex particle method, VPM. It's computationally more demanding than the BMT model, but allows us to look at wake effects and the modeling of multiple devices and arrays. Work will be carried out to validate both numerical models, the VPM and the BMT, against real site data. This will be laboratory scale data and full scale turbines at sea. These are the citations I referenced to, and if you want more details, please have a look. Thank you for listening, and if you've got any questions, please don't hesitate to email me or putting a question in the Q&A function. Thank you.
Yes, thanks, Justin. For those of you who weren't able to read all the references in the 5 seconds they were up on screen, the slides will be circulated to everyone when Carly sends the link around to the video. I'd now like to hand over to Stuart to give us the second talk, the second case study from Tiger.
Okay, hello everybody. Thank you for the introduction. Yeah, so I'm going to talk a little bit about something perhaps slightly different. So I'm going to talk about assessing the environmental impact of turbine blades, and a bit of work that we've been doing on the Tiger project recently. So using a method called life cycle assessment. So first of all, kind of introduce a problem. So in the wind energy industry, there's a lot of turbines are currently kind of reaching their end of life. So whether that's a 20-25 year lifetime, and a lot of the material from those turbines, support structures and things like that, is able to be recycled because that's steel. But we have a problem with turbine blades. So they tend to be made of composites, so carbon fiber or glass fiber. and those are really difficult materials to, or essentially impossible materials to recycle. You can see the numbers there. There's a lot of, in wind, there's a lot of turbine blades being produced. Currently, the options are basically either to landfill them, as you can see in the picture at the top there, to incinerate them, or I mean, you can occasionally make them into something else, like the one on the bottom right there has been made into a playground in the Netherlands, but I don't think that's likely for sort of 20,000 blades a year, but to show what can be done with one or two. But yeah, this is potentially a future problem for the tidal energy industry. I've just sort of roughly calculated some numbers there. If we're looking at 1 gigawatt of capacity by 2030, we're kind of looking at around 6,000 tons of blade material needing to be disposed of. I mean, obviously, this isn't a problem in the first year of installations. This is a problem that arises after the 25-year or whatever it is lifetime of the turbine. But it's a problem that needs to be addressed at the design stage, because those, obviously, those materials don't become more recyclable by being installed. So it's something that needs to be looked at now. So this is something we kind of started considering as part of Tiger. Using a method called life cycle assessment. So this is a method used across a lot of industries to kind of understand the environmental impacts across a lot of categories, not just CO2 footprint, although that is probably the most kind of common one. So yeah, I've listed a kind of few examples there, but yeah, using LCA, we can consider the impact of a product over its whole life cycle, from extraction of raw materials through processing, manufacture, and so on, as you can see along the top there. Crucially, we can also include the end-of-life treatment, and we can look at basically how to improve the circularity of a material as a whole, or we can zoom in on specific sections of a product life cycle and see how those, what the environmental impacts of those might be. So using this method, I've kind of considered some potential alternatives to the carbon glass fiber option for design of turbine blades. So you can see we've got a few kind of options there: steel, recyclable composites, and bio-based composites. So we just kind of look at each one in a bit of detail. Steel is 100% recyclable. In theory, it's a great material like that. It has a few problems when you consider potentially making a turbine blade out of it. It's quite difficult and energy intensive to make a complex shape like we need for a turbine blade. And it's also very heavy. It's roughly about three to four even times the weight of a glass fiber blade to achieve the same strength and stiffness. And that's going to then require some additional upgrades to the turbine, or it's going to essentially force you to modify other parts of the turbine, which obviously will have further impacts on the overall environmental impact of your turbine. Looking at recyclable composites, these are basically made in the same way as a conventional composite with a fiber and a resin material, but the idea is that at the end of life there's a separation process using a chemical process that allows the two parts then to either be reused or recycled. They can't be kind of fully recycled into the same material, so the product that comes out the end of the lifetime isn't a high performance material, so it has to be effectively downcycled rather than recycled, but it can be reused to some degree. Another option may be bio-based composites. So this is using something perhaps like flax instead of a glass fiber, and that can be combined with the recyclable epoxy materials like we mentioned previously. So these are three of the materials that we've looked at on this kind of study, just to introduce them. So we've looked at these materials, as you can see on the second bullet point there. We looked at three turbine blade lengths. This is ongoing work, so I'm going to talk about a few of the results, and there's more to come down the line. Also looked at a few manufacturing options. So VARTM is vacuum assisted resin transfer molding, which is the most common way of making this type of product. There's various other methods, and a couple of end of life options, so incineration, landfill, and recycling for appropriate products. So just to go over the scope of the study that I've been working on here. So this is to kind of be clear what isn't included and isn't included in the study. So we focused on blades essentially. So if you look at the diagram on the right, bottom middle on the right, you can see it says raw materials. That's kind of the starting point. So we've included all the raw materials, the manufacturing them into the blade and transporting the blade to a location where it would be assembled into a turbine essentially. From there, it goes around, and we're not including anything beyond where the blade is incorporated into the turbine as a whole. So we're not including the transport, installation, operational life. removal and dismantling, and then at the point where the blade is then off the turbine again, then we include that again. So that's whether it's processed, whether it's chopped up to be incinerated or landfilled or whatever. So because this is a comparative study, we're using the same scope across all the different materials. So these exclusions, once the blade becomes part of the turbine, are essentially the same across each of the comparisons that we're using. So it allows us just to focus on the turbine. I've also included, as I've said on the left-hand side there, 3 kind of practical measures which bring in those other features that we talked about, particularly in the steel case. So cost is one of them, but also looking at manufacturing complexity. If you make a blade out of a certain thing, does it increase the complexity, or does it influence the rest of your turbine structure? So we are kind of also considering those additional factors. So to go on to some results quickly, so as I've just kind of said there, this model is kind of undergoing refinement through the Tiger project. We're in consultation with developers. There's some developers being involved in this project, which has been great. So we're kind of going to and fro on that to kind of make sure that what I've included in terms of manufacturing processes and things are realistic cases. I've also looked at 18 impact categories at the moment. So including global warming potential, that's your CO2 footprint, also land use, water consumption, and various other emissions, particulate emissions and water pollutions, for example. So this, I don't intend to talk through this. This is just to show kind of the initial output of the results. You can see along the bottom, we've got impact categories there. So if we highlight 3 particularly, so we're going to look at just briefly at global warming, land use, and water consumption for a few different options. Yeah, just to go through the key that we're going to use so you can see it more easily. So blue is going to show the steel. The conventional composites with a landfill end of life are orange, and with a recycled end of life using those additives are in grey. And then we have a bio-based materials following the same pattern. So the yellow shows the landfill bio-based material, and the blue, dark blue, shows the recycled bio-based material. So first of all, we have a global warming data set results here. So you can see, so these are results in terms of kilograms of CO2 emissions per blade. So this incorporates the fact that the steel blade is heavier and various other blades are lighter and so on. So you can see the steel does look relatively good. The current business as usual, I suppose, is the orange, the GFRP that goes to landfill. So you can see if you make that a recyclable glass fiber, that you have an improvement that goes down to the grey. Similarly, if you use the bio-based, you have a slight improvement over the current product, and if you make that recyclable, you can have a further improvement. However, and this is why people just looking at CO2 is perhaps a bugbear of some people. So if you then go to look at another impact category, you can see that it's not quite the same picture. So as soon as you start using the bio-based product, you have a huge increase in the land use. It kind of makes sense if you think about it. So you can start to see that we need to consider these options over all the impact categories rather than just one, or at least be aware of the results across other impact categories. And similarly, again, you can see once you start to look at the water consumption, you can see the steel process has quite a high water consumption. I haven't shown results. It also has quite a high kind of water impact. So in terms of pollution, water pollution and impacts on other wastewater and things, the impact can be quite high there as well. So I'll kind of just rattle through those results quickly. So just to kind of summarize very quickly, steel does perform well on greenhouse gas emissions, but does need to be looked at in terms of water, and is unlikely to be practical on a large scale. We're only looking at it up to the 9-meter blade, not actually considering it for the new larger blades. The recyclable composites are interesting. They improve the end of life, but those additives that are used have their own impacts that they bring along, and the energy used for recovery is an impact as well. Bio-based composites are quite promising in a way, but land use is relatively high, so that would need to be addressed. That feeds into kind of wider issues about whether it's taking land use away from food and all kinds of other huge issues. So that's the end. I apologize for talking so quickly, and I think I've just scraped in another time. If anybody wants to talk about it anymore, I'd be delighted to do so. Thank you.
Yeah, thank you very much, Stuart. We've been quite ambitious with the times for each presentation, so I'm really pleased with the timekeeping so far. Thanks everyone. It's just Andre to go. You've got your and we've left you with your full time 10-minute slot. So if you'd like to talk a bit about the actual work that we're doing at Monitor, I'd love to hear that from you.
Thank you, Michael. Good morning to you all. I'm André Pacheco. I'm an oceanographer from University of Algarve, and I'm responsible for the ETSI device testing at Monitor project. So basically, what we are attempting to do on Monitor is to measure K-resource and environmental parameters. So we want to collect high-frequency oceanographic data, trying to fully characterize the 3D flow patterns, including velocities, the turbulence intensities, and wind wave regimes of the test sites, which are two, Fall of Harness and from Vlug Strait, and then also to compute load intensities in different resource and operational settings by instrumenting the devices following the VMEA analysis, and then relate this environmental parameters with the load intensities for different types of devices. In this case, we are using gravity-based tidal energy converter and a floatable device. The floatable device is the AT platform from Magalhães Renováveis, which is installed at Fall of Harness tidal test site in Orkney. You all know this is a quite energetic site. So average tidal flow typical ranges in spring between 3 to 4 meters per second. Neap tide between 1 to 2 meters per second. So it's a quite demanding site for measurements of environmental parameters. And the mean flows and the turbulence vary significantly between the flood and the ebb tide. The second site is from Vlug in Western Iceland. So we have there the Sabella D10 device. It's also one of the most energetic sites in France coast, and also experience strong incoming waves. With significant wave heights. And here we are testing as I told, the gravity-based turbine Sabella D10. So basically, we have been conducting ADCP surveys in both sites under collaboration with the European Marine Energy Center, with both the device developers and also with the University of Edinburgh, particularly with Brian Seller from Real Tide Project. This allowed to collect high-frequency measurements. The data are now being processed. So we have been running through quality control with echo amplitude, correlation, speed of sound, pitch roll corrections, noise levels, to get the most of this data. We have really nice time series. Then we are running through different methods to wave turbulence separation. The one we think it's giving the better results is the wave synchro squeeze transform, although it's a lot time consuming. Then we are estimating the Reynolds stresses and turbulence kinetic energy density using different methods so that we can compare and determine also uncertainties, which as our catapult reported are quite important for this VMEA analysis. Then we are going to evaluate the TKA dissipation and production through time. And also we are estimating the wave parameters using different methods to get these wave statistics from both sides. So basically, what we want output to our catapult is the tidal flow speeds. So east north up resolve time series, so that we can then choose the data sets we want to explore more. We are also outputting tidal direction and histograms of the site. We are also outputting shear profiles and variability during the tidal cycle, and of course, water depth variation and wave statistics. So sorry, I'm getting here some outputs of the data that we are getting so far. is time series of mean water depths, as you see in the upper right corner, current velocities, time series, also current direction, the different velocity components, and then of course the TKA density through through time using different methods, getting shear profiles and velocity profiles. This is high turbulence measurement, so this is quite time consuming to get, but we are getting values of 1 Hz and 4 Hz frequency for all these variables. The problem has been in a monitor is how to get simultaneous measurements with of the load parameters, because we have been facing several problems, and this pandemic didn't help on getting the devices on the water. So both devices are now on dry dock and are being instrumented to try to fulfill the second part of this project. We have some load intensities parameters that we have determined, and we want to compare this with the environmental parameters. So what we are trying to do now is to classify the load data into categories and try to then match those with the velocity turbulence measurements. For this, our approach is to try to rate the change of the tidal range and then create probabilistic distributions so that we can compare the loads that we obtain from previous deployments and some data that developers already gathered with the environmental parameters. So I think I'm inside the time. So thanks a lot for your attention, and thanks a lot for listening.
Great, thank you very much, Andre. Everyone has kept really nicely to time. Thank you all for your work on that. We're now moving into the Q&A and panel session part of the event. Of course, I hope you've seen that there's been some questions coming up on the Q&A part of the chat, which have been answered as we got to. So we do have an opportunity now for any other questions from the audience to go into the Q&A. We can answer that now. Otherwise, if there's any other questions that the panel members like to ask to each other, I have a couple of questions I'd like to put to Philip and Stuart. And if anyone else has any other questions, then it'll be a good time to do it. And then after that, we'll move on to a little panel discussion about how reliability will inform research and particularly industrial academic collaboration going ahead over the rest of the lifetime of the projects and beyond. So the first thing I'd like to ask was to Philip. I think with the results that you've shown are very interesting, particularly looking at the kind of the failure rate as the number of hours increases. And you did mention that, of course, we're in a situation where we're, compared to onshore wind just now, we've got a lot less data to be working with. So in some ways, it's difficult to draw conclusions with the same degree of certainty as you can for a more mature industry. I wonder, though, if you've got any feeling about whether the data that you've shown, which is collating lots of different types of technology together, so you've got floating devices, fixed devices, piled devices, and you've also got horizontal axis devices and vertical axis devices. Would those tendencies look a bit different if you separated those technologies out in some way, do you think?
Thank you, Michael. We've done some further, I haven't had time, but we've done some analysis on kind of how the different technologies perform, and kind of what are there any relationships between, say, any of the technology features and the way the project fared. In terms of the data set, I mean, it's, not sure if you can hear me, I need to pull this down, that's better, I hope. So we've done some analysis looking at the different technology features to kind of tease out how the project performed. In terms of the failure rate, kind of the word of warning is that it's somewhat an unconventional failure rate definition. So typically you define the system as, say, the single turbine, and then count the number of failures over its life. We kind of, because we haven't got that data, we made the project, if you like, the whole installation project a system, and then just asked over its lifetime, did it kind of, because you can then go and fix it, did it overall perform successfully, or did the project fail in some way? So the failure rate is not directly comparable. I guess if you do that for wind, in the early stages, there are examples actually similar where they wind. There's a famous project in Germany called the Grovian, where they jumped from kind of kilowatt feasibility and wind turbines that worked well to, okay, we'll now jump to megawatt installations, and the forces and the moments were just outrageously large, and that project as a whole failed spectacularly. Although in hindsight, that was kind of the nucleus of the wind industry in Germany. So the engineers that went with it thought, no, the technology works. We just went too big, too quick, and then they went back and kind of really went up the technology ladder there. But hopefully, we'll be in a position to have more reliability data as we go forward. Because that is really needed on a subsystem level to improve those.
Yeah, I think it's interesting talking about the looking at the failure not at the level of a device, but at the level of a device deployment, kind of the whole thing. Because if you can't get the device out, it doesn't matter how reliable your device is. If you can't get out if you can't get it out of the water or bring it back to shore safely, then you can build the most perfectly reliable device in the world, and it won't make a difference. So I think it's useful to have that kind of scope in mind when you're talking about reliability. And Stuart, as one thing I wanted to pick up on the presentation that you gave. I was intrigued to see that the land use went up so much when you start talking about recycled material for the blades, and I wasn't quite clear on why that was the case.
Thanks. Yeah. There's a lot of kind of external other influences that you don't necessarily see. So I think one of the ones where the land use jumped up when it was recycling was if you look at the recycling of the bio-based product, because it's to do with, because that needs, that the recycling of that is essentially a biodegradation process. So in order for something like that to biodegrade, it actually needs additional organic matter to be kind of mixed in with it in a heated process to allow it to actually biodegrade. It won't biodegrade on its own. It's just, it can be biodegraded by something, but it doesn't have the capacity to do it itself. So then additional stuff essentially needs to be grown and mixed in with it. So the land use will be for those additional crop products that need to be grown, or that need to be, you know, they can be waste products taken from another process, but they still need to be kind of allocated to this. So yeah, it will be the additional products that are required to kind of facilitate that biodegradation.
And that applies for not just the biomaterial, but also for the standard carbon fiber composite, because you showed a similar increase in land use with the recycling there.
Okay, so no, that would apply for for any of the biodegradable cases or the bio-based products, yeah. But even when they used the conventional resin, but for the so the recycling land use for recycling, I'm just going to have a look at my data and see the. So it was interesting to present these things because people spot certain things, and then it means you kind of go back and look into them and trying to see. So yeah, so for the recyclable glass fiber is a little higher. So I suspect that must be something to do with the additive, because the only difference between the conventional and the recyclable glass fiber products is the use of the additive. So there could be a biological component in the additive, I suspect. So it's something that needs to be grown somewhere and then brought and used to create that additive. So I would imagine that it's a kind of upstream impact of the use of that additive.
Okay, great. No, thanks for pointing that out. It's something that you don't necessarily think about. You know, I don't. It's not something I would have thought about. I hear, oh, it's such and such a product or such and such a material is biodegradable. Oh, great, fantastic, good news. It's only upsides, and then not really seeing the full kind of whole system impact of what that means in terms of what trade-offs that requires in order to achieve. Okay, right. I think then it might be nice to have a brief discussion among the panel about the topic that we mentioned and the role that industrial academic collaboration has to play, particularly when we're looking at reliability modeling, because from the point of view of the Monitor project, we've got 2 industrial partners on board who are at the stage of deploying individual pilot devices. And it's been invaluable having them on board, being able to have access to this kind of real data from an actual turbine, because in some ways that's the fundamental gold standard. You know, whenever we're doing our lab work or numerical work, we're trying to get what we would get from a real turbine, just in a more convenient way. But of course, we have to balance the getting this kind of gold standard data with the simultaneous need for confidentiality, and it is a tricky balance. It's something that we really can't get a better data set than that. But then it's very difficult to share it and to talk about it. And of course, as academics, we're strongly motivated to do so. That's you know, we want to put out as much data as we can. So I wonder how you think this kind of collaboration could be improved to further improve reliability. Is it better to build individual reliability models for each device, or is it better to work with a generic reliability model that uses anonymized data as much as possible?
Yeah, maybe if I start, Michael. So I think there's a few items there. So I think at the company level, I think each company hopefully runs an FMEA at the very least, if not a reliability model of some kind that draws on available data, but primarily on their experience going forward, because that should be a living document. So I mean, as the FMEA, or if you do a VMEA, that should be continuously updated almost with every step in the development and every test they're making. But they can't do it all. And as the sector goes, and I think where there are kind of cases that reliability databases have been established, they're always to the benefit of the wider community and the sector as a whole, if some of that kind of competition is overcome. So it's a classic economics problem of the kind of the common good. But the Catapult is making efforts certainly on the offshore wind side to bring the stakeholders together there and to kind of submit to the data pool as an independent source. The incentive for companies to take part in this is obviously they only get access to the data if they're part of that circle, which is causing issues on the academic side because we don't get access to that data. So we have to rely on other sources. And I think where the academics can come in, and there's good precedents for that in other fields, is to act as kind of third party without a vested interest, to take care of the confidentiality and not name and shame anyone, but really to work on the benefit for the sector, to say what are the failure modes, what are the frequencies, because reliability as such is not a binary. I mean, we try and tend to judge as binary, but in the design process is always what you would do in an FMEA, what is the risk and the likelihood, and what is the consequence, and that gives the risk overall. And then you have to see, okay, do we mitigate that, or we just let it allow to happen, and then we can think about maintenance for those items. So you really need to have an idea of both what are the failure modes and what are the likelihoods. So yeah, there's work to be done, and hopefully within projects, I think that's the third point. There's some room for that as well. So it doesn't always have to be either a database free for all or one-to-one. It can also be sharing kind of within a larger project, and hopefully for Tiger at least, I'm hopeful that that's a good platform to do so.
Yes, of course. I think monitors on a significantly smaller scale than Tiger is. So we've not got the same kind of size of number of industrial partners who are involved, but we've got the two different developers who have been involved, and I think them being able to speak with one another on the same kind of reliability project has helped both of them improve their own reliability modeling. I think we're only got about 3 minutes left or so. I think if there are any last minute questions from the audience, I hope you're frantically typing away, because we're not going to have that much time to answer them. The other thing I would think it's interesting to think about is the scale of the industry. Obviously, these kind of FMEA and VMEA models were developed for industries that were much more mature and had a lot more data to work from. So I think the question of how useful they are now, and whether we can look forward to them being more useful as we step to maturity and have information from a wider range of projects, and therefore whether we ought to be thinking about the directions we need them to go in now to maximize the benefit that we get from them as we increase the size of the sector going ahead. What specifically do you think, and maybe Alistair, someone who's worked kind of more hands-on with the VMEA model, what specifically do you think the most important priorities are to make sure that the models are as useful as possible as the sector expands in size?
Well, increasing our pool of input data for certain, and then understanding from the industry where the most value can be gained, because you can look at many aspects of tidal devices, from our sensors or connectors or blades. There's loads of technology that's designed and new and difficult, and focusing on the bits that will give us the biggest steps forward in the early stages are really key. So understanding what that is, and then fueling those studies with good, reliable data.
Okay, great, thanks. Well, I think there is just a minute left now. So if there's any last minute comments from anyone in the panel.
Yeah, on the FMEA, maybe, Michael, because and that's partly where I think some of the challenges lie as well, because a good FMEA lives off data, yes, for sure, but it also lives off kind of the team that conducts the analysis. And in other industries where you have much larger engineering teams with more experience, maybe we've got experience across the sector, we've got experienced engineers, but typically the companies developing these technologies are SMEs. So they will not have the full engineering team. There'll be a lot of subcontracting going on. So that's sometimes a challenge to actually bring together all the stakeholders and all the experts that will have the empirical knowledge of, if you do this or that, what is going wrong and how likely is it? Because it's relying a lot on that kind of qualitative, famous engineering judgment, if you like, to mitigate some of those.
Great. Yeah. So it is in some sense not just a matter of the data that we can feed the models, but the data that the teams implementing the models are familiar with. Yeah.
So anything we can do, I think, across the sector to promote lessons learned and kind of actually be open as we can on failure modes and what things have gone wrong, because that avoids others to do it, or at least to look out for it.
yeah, we've got to try and avoid duplication of effort as much as we can if we want the tidal sector to become more reliable in the future. Okay, great. Well, I think we've reached the end of the webinar. So to remind everyone, the recording of this will be made available up on both project websites. Carly will circulate an email to everyone with the link to those videos when they're available, along with the chance to download the presentations or most of the presentations, except for some things that are still being considered for publication. And also a chance to sign up for the project newsletter if you haven't already seen a link for that in chat. Thank you all to everyone on the panel and to all the audience members. I hope you've had a good morning/afternoon with us and enjoy the rest of your day. Thank you all very much for coming.